for the introduction. Thank you, organizers, for this very stimulating, amazing workshop, getting us all together. And thank you, Ian, for setting me up so nicely for my talk. So I'll kind of be continuing this idea of what happens when you try to cool these molecules that have interesting properties, but they also have certain adverse properties that make them difficult to laser cool. The property I'm talking about is predissociation that Ian touched upon. And the molecule of interest is calcium hydride. So maybe first of all, I'll tell you guys why we want to work with calcium hydride. So at a very basic level, you can use experimental data that you obtain from studying a molecule like calcium hydride to benchmark quantum chemistry calculations. So most of my talk is going to be pretty much that today. But imagine once we have cooled successfully calcium hydride, we can study chemical reactions. We can study cold collisions between calcium hydride and itself, between calcium hydride and an alkali. So for example, there are proposals for how you can do evaporative cooling with calcium hydride and lithium atoms. And then, of course, the thing that Ian touched upon is that we could dissociate in a controllable fashion this calcium hydrogen bond and give rise to ultra-cold hydrogen, which then is like a very interesting avenue for precision measurement. In fact, I'm just flashing the slide. Ian has just mentioned it. The original idea that we came up with is that if you're careful about the fragmentation energy, so you basically want to dissociate into this state where the center of mass energy is as small as possible, then your fragment will not speed up. The light fragment will not take a ton of kinetic energy, and it would be even actually cooled further than the parent, just by the ratio of the mass of the parent molecule. So calcium hydride seems on the surface very similar to other molecules that you've heard about in this workshop. Calcium fluoride, for example. The electronic structure of calcium hydride looks very similar. It's a doublet sigma ground state, and you have the lowest doublet pi excited state, and then you have the B sigma state. The transitions are fortunately very visible. Like it's easy to get laser diodes at these wavelengths. Because of the light mass of hydrogen, although some of the energy scales are much bigger than calcium fluoride, say. So for example, the spin rotation splitting of the ground state is close to 2 gigahertz compared to tens of megahertz for the other molecules. And then the hyperfine is quite resolved in the ground state. So you have to worry about all of these transitions, and you have to couple them to the excited state. So you need sidebands on your lasers. But we know very well how to do that. And fortunately, the hyperfine in the excited state, in the A state, is unresolved. So that helps with exerting forces on the molecule. The one thing that I would like to point out here is note that the binding energy of this molecule is actually smaller than the lowest excitation energy. So the lowest bound excited state electronically is above the ground dissociation threshold, which is something I'm going to touch upon in the second part of my talk, which will lead to predissociation. Okay, so in the beginning, what we wanted to do is we wanted to set out and confirm that this molecule is indeed laser coolable. And there are a few properties that are crucial for laser cooling, and you guys have heard a lot of discussion of those properties. The first one is that the molecule should have quasi-diagonal branching ratios. So we want it to be as close to a two-level system as possible. So to do that, what we do is we take our standard cryogenic buffer gas source, and then we detect the molecules farther away, and we use a laser that is exciting to the X to A or the X to B transition, and we use 2 PMTs to now collect photons at 2 different wavelengths. So let's say that one wavelength acts as our reference, and the other one is a vibrational decay channel. And by counting how many photon goes to each PMT, we can actually estimate the branching ratio. So this table actually shows the branching ratios we measure for the A and B state, and they're pretty good, and they match with theoretical predictions that had been around for a while. And they also have this very good property that they sort of collapse very quickly. So as you go to V equals 2, you've already suppressed your branching by 2 orders of magnitude, more than 2 orders of magnitude. So this is a good property for a laser coolable molecule. But that's not enough. Not only do you need good branching, you also need to be able to scatter photons a lot of photons very fast. So what you need is a good scattering rate. So fortunately, we knew the lifetimes of these states. So the A state, as I mentioned in the previous slide, has a 33 nanosecond lifetime, which is actually a pretty good lifetime when it comes to scattering rate. Calcium fluoride has order 20 nanosecond lifetime. But we confirmed it experimentally by creating sort of a multi-pass interaction region along the molecular beam path. And then controlling the number of passes, we can see how much, we can vary the interaction time and see how long it takes for molecules to get depleted to higher vibrational states. So first, we just apply the cycling transition. We see this exponential decay pretty rapidly because it only takes about 20 photons to go into this state. And then we repeated this measurement but added this repump transition. And now the combined VBR of this state allows you to scatter 100 plus photons. And we see that it decays rather slowly. But from the exponential fit in both these cases, we can predict that it scatters at a rate of about 1.6 million photons a second, which again is a reasonably fast scattering rate for laser cooling. Then the last thing we wanted to study is, okay, let's try and actually laser cool this molecule. All of these initial experiments that are sort of in the small sort of beamline experiments, you're not able to scatter a lot of photons because you're usually limited by interaction time. These molecules are zipping by. Even if you can scatter 1 million photons a second, you have a very short amount of time, like order milliseconds, to interact with it. So what we do is we use this effect called the magnetically assisted Sisyphus effect, which kind of magnifies the forces that you can apply on a molecular beam, and you can measure a very significant change in size by scattering only order 100, 200 photons. So that's what we do in our experiment. We were able to take this is the beam profile, so this is what I show. In this direction is where we apply forces on the molecule. The molecule is traveling left, right. What we see is that the unperturbed beam profile, which is green, can be sort of narrowed for blue detuning or broadened for red detuning, which is a signature of subdoppler cooling through the Sisyphus mechanism. In fact, we vary parameters as we do that. So basically, we measure this change in size as a function of, let's say, detuning. And you see this classic inverted profile, inverted Doppler profile. Then we vary the intensity, and we see that for the intensities that we had available to us in the lab, we were far from saturating it. And then we also see a well-known magnetic sort of shape that you need a small finite magnetic field to actually see this effect, because you need to match the remixing rate with your scattering rate. But at high fields, it also gets suppressed. So all of this was convincing enough for us that we can, in fact, scatter order 200 photons on these molecules at a rate of about 1 million photons a second, and we can cool in one dimension by a factor of 2. So this is essentially like the building block that proves that you can continue doing further laser cooling. But laser cooling to get to MOT requires scattering many more photons than 200. In fact, for our molecular beam, we expect to need to scatter about 20,000 photons to get to the MOT capture velocity. So things are a little different when you go to that regime. And that's where the idea of predissociation comes in. So predissociation is something that chemists have known for a very long time. Physicists also have, but haven't thought about it too much. And it's a very well-known common phenomenon. And here I found this paper that shows sort of standard predissociation pathways of astrophysical interest. And there are, for example, this simple case you can imagine that you excite to a state that actually is unbound. So your molecule will roll down the hill and dissociate into fragments. There is this other case where there is actually a crossing between states. And then if you are unfortunate enough to couple to a vibrational state, it can tunnel into the other state or adiabatically cross over and leave. So there are all of these known mechanisms of predissociation. But if you look at the diagram of calcium hydride and focus on the bottom of these potentials, this is where we are trying to cycle photons. Nothing of this nature seems to be happening around there. So the mechanism of predissociation in our case is actually a much more simpler sort of basic thing that happens, which is kind of just a coincidence. It's a coincidence that some discretized, quantized vibrational levels are almost near in energy to continuum levels. And this just happens because the excited states are above the ground dissociation threshold. Most molecules like calcium fluoride or strontium fluoride, they don't have this problem until they go to very high vibrational states. So what can happen is that you can have radiationless transitions where your molecules just have a finite probability of crossing over, of tunneling over to the state where they're dissociated. And this is actually a nice graphic that Chi, the grad student on the project, made for DAMOP, so I thought I'll put this in. This is the state that is our ground state, our lowest excited state here in A, and then the B excited state. And you can notice that they're all above the ground continuum. This has been confirmed by new calculations that our theory collaborators have done. And what happens is these radiationless, non-radiative transitions are now allowed. But a transition from the pi state to the sigma state is actually nominally forbidden by a very simple sort of no-crossing rule that is rigorously true for diatomic molecules, that if you have level crossings in diatomic molecules where they have non-similar, non-identical symmetries, they will just cross each other. While if they have similar symmetries, they will form an avoided crossing. So what that means is that this particular decay pathway is nominally not going to occur, which on the surface is good news because this is our primary cycling transition. However, we cannot say the same thing about the B state. The B state is also a sigma state, so that is nominally allowed. So what we wanted to do is figure out a way to directly measure this in our experiment. We came up with this very simple scheme to measure the predissociation rate for this B state with 0 vibrational quanta, under the assumption that this state does not predissociate. And I'll mention why we need to make that assumption for now. So what we do is we start by measuring the population in our ground state. Then we scatter photons on this transition repeatedly, so we cycle photons, so that maximally get population transferred into a higher vibrational state. Then we pump the population back and measure how much came back. So we have an original number, how much went away, how much came back. Now we repeat the same process on the A state. With the identical system, identical lasers, we just make sure that we can assume safely that the A state does not predissociate at the same level as the B state. And use the numbers that we get from the A state as a way to calibrate the efficiency of each process so that we know that, yeah, sure, some molecules will be left behind, but we know roughly how many will be left behind. And then the other assumption we make is that the VBRs are known. So the branching ratios are known. So what we are trying to do here is we are trying to do a consistency check. If our VBRs are what we think they are, then the population distribution should be consistent. If they're not consistent, we are missing something in our estimation of VBRs. And that something is predissociation. And I mentioned that because remember the way we measure VBRs, we have no way of detecting fragments that come out, especially because it's a radiationless transition. So when we measure the number of photons in each trajectory of decay, that particular pathway is completely lost. So in the end, what we do is we add up everything we measure and we say that that number should be 1, but in fact that is not 1 because there are some molecules that were just lost. So this is kind of like the basic idea of this measurement. Now you can do the same measurement for the V equals 1 state, and this was actually motivated. And in the beginning, we had no reason to believe that the V equals 0 state and V equals 1 state will be wildly different in their predissociation. But we got some very interesting input from our theory collaborators that this might be more predissociative. So we set up with an identical sort of scheme to measure this, and it goes very similar ways, but first we actually optically pump the population into this state, and then we do the same gymnastics of scattering photons on this transition now, and now we have 2 major decay pathways. We can repump one of them at a time and measure how much comes back. And again, we treat this transition as our reference and measure the same quantities again. And of course, we also go with the assumption that the measured VB or the calculated branching ratios are correct. So self-consistency check. So here's what a typical data set looks like. We have to be very careful when taking these data because buffer gas systems are known to be they fluctuate a lot. Like numbers are not a very well-defined quantity in these experiments. So we have to measure ratios very carefully. So what we do is we interleave every measurement with a measurement of a reference signal. So basically an unperturbed molecule population. Then we do another sort of run with a different configuration, then again interleave that, so on and so forth. And we do this over hundreds of cycles until we know that we have converged in our errors. So this is what a typical data set at the end of averaging would look like. And this is what the error distribution, or so this is like the data distribution of the individual ratios. So each quantity we measure, we calculate the ratio to our reference, and then we basically average until we see convergence. And then we confirm that the distribution is somehow normally distributed. So using all of this, now we can estimate, using the known VBRs, what, if any, is a predissociation rate that you can assume or expect for the state. And the metric here is that if this number is significantly outside of sigma, then there is a missing number. So that's our metric, that if this is 2 to 3 sigmas away from 0, then it is something. What we find is that it's a 0.1% effect for the v equals 0 state, which on the surface seems really small, but we're very surprised that we can measure this. However, when we measured the v equals 1 state, it was far more dramatic. We measured a 7% effect. We were not expecting an order of magnitude more increase in this predissociation. But after talking to our theory collaborators, it turns out that that is to be expected. It is something that people just don't think about that often. So our theory collaborators went ahead, especially Claire, who's the lead on this, they went ahead and calculated the potential energy surfaces. We gave them our data to sort of calibrate and check and confirm that they can reproduce Frank Condon factors that have sufficient good overlap with our measurements. And then once you know the potential energy surface, you know the wave functions because you've calculated the branching ratios, the only thing left to do is calculate the continuum wave function. So that's a little tricky, and I think Claire is going to touch upon this in her talk. And then you can calculate the predissociation rate by using this simple Fermi golden rule picture that you have a density of states, and there's a coupling matrix. So you have the wave function in your continuum state, which is characterized by energy because it's no longer quantized. And on the right, you have your discrete vibrational wave function. And then you have a coupling matrix that you have to figure out what that coupling matrix should be. So I will leave it to Claire to sort of shed some more light on that. But basically, Claire did the calculations. And this is preliminary. This is still work in progress. But what she finds has very good, or within order of magnitude, agreement with our experiments. In fact, the thing that is the most alarming is the fact that theory also predicts this order of magnitude higher predissociation rate. In fact, as you go to higher vibrational state, it keeps going. It exponentially rises. We are still trying to figure out how far that goes. There are more intricacies in the potential energy surface that leads to interesting behavior. But this is something that we are currently working on. This is very interesting for us. Now, the question now is, can the A state predissociate? Because I said that it's nominally forbidden, but of course, there is spin orbit mixing. So the B state, there is a state in the B manifold which has exactly the same J quantum numbers and other things as the A state. So they could mix via spin orbit coupling, but it's a weak effect. And I'm not going to go into the details, but you can basically rewrite the basis vectors of the A and the B states and write it in the spin orbit coupling matrix and diagonalize it, do the same for the V equals 1 state. And you can kind of calculate how much B state character is imprinted on the A state for both the V equals 0 and the V equals 1 state. So we find, for example, that only about 0.06% of the B state gets imprinted there. So predissociation also gets scaled down by that factor. But for the V equals 1 state, it is slightly higher because the energies are a lot closer. And I won't, again, go into details on this. But what it means is that we can kind of predict what is a bound on our predissociation rate for the A state, which is our main workhorse cycling transition. what we find is, or what we calculate is, that it's actually pretty small. So 10 to the minus 6, 10 to the minus 5 level predissociations, which, again, on paper seems very small, but let me try to put this in perspective. So imagine that we were cycling photons on our X to A transition for laser cooling, and then none of the repumps existed. This is a clean system. What I have here on the left is, or on the y-axis, is the fraction of molecules that remain within your cycling as a function of the number of photons you scatter. If the A state was perfect, this would be a straight line at 1. But the A state is predissociating at the 10 to the minus 6 level. And if we use a metric of saying that, okay, after how many photons half of my molecules have been lost due to predissociation, I get an estimate of about 1 million. Now, for those who have laser-cooled molecules, you know that 1 million is good. You're fine. If you can scatter 1 million photons, you're way beyond your MOT. So this is not a problem. But you cannot live in a world where you only have one laser. You need to repump population out of here. And again, there is a practical reason why we don't want to repump from V equals 1 to the same exact excited state, the AV equals 0. Because once you add that repump transition, now you have double as many ground states coupled to the same excited state, and you get a reduction in your cycling, your scattering rate. So we would ideally want to go to this state, if possible. And so we can estimate now, with this laser added and the 0.1% predissociation there, what do you expect? Well, you now lose 50% after scattering about 20,000 photons, which for us was a relief because 20,000 photons is roughly how much we need to get to a MOT. And losing half of our molecules is not a big deal. Usually from our beam, we are able to capture at most 1%, less than 1%, way less than 1%. That is what we capture into a MOT. So it's OK if you're losing another factor of 2 in the mix. That will be my claim here. But things get very complicated if we now start adding higher repumps, because as I mentioned before, this state is even worse. In fact, what you see is that now you cannot even scatter 10 to the 4 photons. So that's not good. Our conclusion is, do not repump through a higher vibrational B state. Instead, we can now repump through these states, because repumping through the AV equals 1, 2, and beyond has no effect on our scattering rate. And these states are definitely much better from a predissociation perspective. So that's what we have decided is the proper way forward to reach like a MOT of CAH molecules. So that's where we are headed right now. In fact, we just received our high-power cycling laser from Preci Lasers that can get us 3.5 watts at our X2A transition. So we are very excited about that. We have come up with this scheme of using AOMs and EOMs and the single laser frequency to create all the necessary sidebands we need for slowing and MOT. So we will perform white light slowing as our preliminary way of slowing. And we have already made these EOMs that have sidebands that spread over the entire velocity spectrum. We are going to start out with AC or RF MOT coils. Again, this is identical to the MOT coils that calcium fluoride, calcium OH have used. We are not trying to reinvent anything here. We know we are going to do what works, what we know works. And we have all the vacuum components ready for assembly, which is our next phase now. Just to flash this quickly, this is data that we got right before coming to the conference. We, for the first time, measured directly our calcium hydride beam velocity through a very interesting technique that I can talk later about. But essentially, we find that it matches the calcium velocity that we measured just directly. So the peak velocity is around 250 meters per second, which is a little bit high for a single stage source. But we know why that is. We are running in a configuration that optimizes signal and not, or flux, but not velocity. But we are going to do vacuum upgrades now to try and minimize this velocity. So we start out as slow as possible and actually have less burden on laser cooling. OK, so with that, I would like to thank my team, theory collaborators, granting organizations, and thank you for your attention.
About so your next step of slowing the beam and putting the MOT chamber on the beam axis, so you have a forward velocity and a scattering rate. whereabouts are you going to put your Mach chamber, and
Oh.
what kind of safety factor are you going to build in?
Yeah, that's a very good question. So what we are doing is we did some very basic calculations of a scattering rate from our white light beam, and we found that we would need at least half a meter of slowing length. But our cryostat was not designed with that in mind, so there's a lot of dead space inside. So in the beginning, the Mach chamber is going to be very close, not leaving a lot of space for differential pumping. But if needed, we will just add extensions here and push the Mach farther, depending on how much slowing length we need. But half a meter to 750 centimeters, something like 75 centimeters would be our guess. Yeah. Yeah.
Do you have a general feeling for, especially if you think extending to polyatomic molecules, what type of systems might have predissociation issues versus might not? Is there any qualitative role that you can?
One thing I learned from this, Ben, is that being a diatomic, it saved us. Polyatomics would actually not have that Wigner no crossing rule, and anything that can happen will happen in a polyatomic. There's so many other couplings. So a priori, I would say if you have, if you have any coincidences by any chance, it's going to be bad for the molecule. But I don't have a deeper intuition.
For a bigger molecule, essentially just the energies are would be a good starting guide?
Yeah. Just like knowing what the, how the density of states is. Yeah.
How coincidental is it in the sense that, like, do you know if this sort of predissociation feature would happen in, say, strontium hydride or, beryllium hydride, et cetera, or is it just calcium hydride happening to be unlucky?
No, very good question. Barium hydride doesn't have this problem. So Ian showed a potential energy surface. Actually, it is well confined within, the cyclone transition is well confined within the ground state. It's the mass of the alkaline earth that leads to this problem. So beryllium, calcium, and magnesium would have this problem. Strontium is right on the edge. I think it's still not 100% sure, but it most likely does. But barium and radium don't. So.
I'm somehow missing this link between the non-crossing rule and the predissociation. The non-crossing rule just says that the potential energy hypersurfaces cannot cross, but the predissociation means that you need the kinetic energy operator in order to come between the two. So what's the direct link? The other question would be, do you see a dependence on the rotational state for your predissociation?
That's a very good question. I'll answer the second one first. We haven't investigated the rotational state because cycling only works on one rotational state. So all of this is for n equals 1 in the ground state. It's a very good question. We do not think that we'll be able to scatter enough photons to amplify the effect of this predissociation. So I don't know how easy it would be to measure, but I guess we can ask our theory collaborators to look into it. What I know is that the centrifugal barrier can play a role, but that most likely matters in the excited state, not the ground state. So not 100% sure. The first question was, how does the no crossing rule lead to this? I'm just trying to give like my intuitive picture of it. If there is a crossing that is like just a crossing, not avoided, then what it means is that the states are not talking to each other. There's no coupling between them. So there will be no matrix element that couples a wave function from one basis to the other basis. While if there is an avoided crossing, that means there is a finite coupling, and that you can actually have either an adiabatic transfer or you can have something that excites that. Like there is a finite matrix element. This is my understanding at a very basic level. Yes. Thank you. Thank you.
Can you have direct predissociation off of the X continuum?
Oh, that's a very good question. So I think Eric's question is, if I can get there. That's a problem with animations. It takes forever. I think, Eric, your question is, can we go from here directly there? Yeah. So that's something that we want to pursue. The wave function overlap is going to be horrendous. So I don't know if it's going to be feasible, but the wavelength is actually very good. It's like 700 nanometers, 700 something nanometers. We can get arbitrarily high powers in principle there. So I would like to see if it is possible. But.
Well, I just meant that it could also be a lost channel.
Oh.
But yeah.
Sorry. Yeah. Yeah, no, because the end goal of this is still to dissociate the molecule, or one of the end goals is to dissociate the molecule. So this is something that we think actually is going to play in our advantage going forward. The B state being predissociative also means that as you go higher and higher in the B ladders, you're getting more and better overlap with the continuum wave function. So a better overlap with the continuum wave function means a better matrix element, which means you need smaller laser power to couple these states. So we imagine that doing some sort of a 2-photon process where we do a single excitation one to a higher vibrating B state, and then a second photon that kind of brings it down adiabatically, so like a stirrup process, might be a way to controllably take the molecules from the ground state and put them in like really the lowest energy, kinetic energy continuum state, which is kind of like the next thing we want to pursue. But of course, a direct excitation could also work to break the molecule, but we don't know if it's feasible.
One more? I have a fairly technical question. So the laser scattering, photon scattering rate in your laser cooling was 1 megahertz.
Yeah.
That's quite far. I mean, to optimize laser cooling, I believe the photon scattering rate should match the time the molecule travel through the product.
Oh, in the Sisyphus cooling process? Yeah, so what I did was I kind of conflated a bunch of things. This is basically saying that you can scatter 200 photons at this rate on resonance. That's like just my plain laser cooling thing. For Sisyphus cooling, we scatter at a much lower rate and also lower number of photons because we are off resonance, right? The maximum effect is at a 20, plus or minus 20 megahertz detuning. So that factors in and reduces this number. Yeah.
All right, let's thank all the speakers of the session again.